Hello everyone, welcome to Natural Language Processing, word embeddings, and also the advanced pre-processing techniques. And in this session, we will be discussing about some major advanced text pre-processing, which we are going to do to our text. If you remember earlier, we have seen few more pre-processing, which is the very much basic. And especially when you turn them into numbers, we are trying to give some meaning to those numbers or try to convert the text into meaningful numerical representation. But whatever we have done with bag of words or TF-IDF is not enough because they just tell you out of your entire document what is their frequency. It's a frequency based method and it is based on different methods, right? For example, based on the frequency, whether you count how many occurrences it has in each sentence, that's bag of words. And if you calculate the term frequency and the inverse document frequency, then it is TF-IDF, and we do both of it. So with these things, now we are going to move into advanced steps where we try to convey the message, the text into numbers in a more meaningful representation. So we'll be starting about word embeddings now. So word embeddings are a way of representing words as vectors in a multi-dimensional space where the distance and direction between vectors reflect the similarity and relation among the other corresponding words as well. Consider maybe if you are trying to represent words in a vector in 2D or 3D format, and what you can do is once you plot them, you can tell based on the distance and direction, you can tell whether they are related or not. For us, we know that Moscow is the capital of Russia, Madrid is the capital of Spain, Rome is the capital of Italy, Berlin is the capital of Germany, Tokyo is the capital of Japan. So this should be passed, okay? And we have some words such as king and queen, which is related to monarchy, kingdom, where we have man and woman, and some things like if you have a new word, something like burger, which should be somewhat not nearer to any of this because that's a food item, and this representing the male, female, or towards hierarchy or monarchy and all, right? And we have verb tense, and also in this way, instead of just going with frequency like we used to do with our bag of words or TF-IDF, if each word has a number and those numbers have other words which are related to that number as well, so they are nearer in that number. So in those ways, it will be really helpful and meaningful as well for us to process it. So that is word embeddings, which we are going to see now. And when we talk about word embeddings, the frequency based method is also coming under word embeddings. So the first type is frequent based, which we have already used, which is one hot encoding or bag of words or TF-IDF vectorizer. So these are frequency based on its occurrence we are going to give. Whereas if you go with prediction based like deep learning methods such as word2vec or some of the methods which is going to help us in converting the words into vectors in a more meaningful way, so that the vectors, the values with their, if you represent them in a multi-dimensional space, then the distance and direction between vectors reflect the similarity and relationship among the corresponding words as well. So word2vec is a NLP technique. As we'll see about, we have seen about frequency based. Now we'll discuss about prediction based like deep learning methods like word2vec. So word2vec is a natural language processing approach that includes learning vector representations of words known as vector embeddings or word embeddings. And these word embeddings can record semantic link between words. Something like king and kingdom has relation, right? Or king and queen. So these are related words. Maybe something like food and banana, they are related because you need to convey the semantic link between words, and this can be done in a more effective way with word2vec. For example, the vectors for the words such as king and queen can be similar because they are both related to royalty, and this method has been utilized in a wide range of applications including language translation and text categorization and so on. So first let us understand about how word2vec actually represents a word, how you can convey the meaning and carry. Then we'll see how it is implemented. If you want to know how it is implemented, the theory behind it, how it is actually achieved, we need to know about its types, which is continuous bag of words or CBOW or skip grams, which we'll see now. So before that, we will go into whiteboard and discuss elaborately about word to vec. So let us go into the whiteboard and let us start with the example. For example, once again, this is actually from Google. So this word to vec is a technique which was introduced by Google. We will be using the pre-trained model from Google as well in the upcoming sessions. So when we use this word to vec, for whatever word you have, it is going to represent them as a vector. Maybe something like if you have a sentence, something like this is not a great product. So for each of this word, it has been trained on a vector. Okay, so it is going to be something like, let us keep a size of 300. That's what minimally they will be having. So a vector with 300 points will be there, and whatever word you pass, what this word is related for each of these 300 words, it is going to be related with some numbers here. Okay, it is trained using deep learning. So like that, for every word it is going to be giving out. Let us do some example like this. Maybe we'll do some detail. So we are not going to consider all these 300. It's complex. So first, for understanding, we are just going to consider some few words. Let us take something like in our 300 vector, let us have a word known as authority. So authority is a word, and then we have another word known as event, and the other word has known as has tail, and then another word known as rich, and then another word known as gender. So this is our training which is going to be reflecting here. So now my data, what do I have in my data? Let us look into our data. So looking into our data, we will be having something like let us write it in a different color then. Maybe something like blue color. Here let us go with my text has something like battle. Then I have a text known as horse. Then I have a text known as king. I have a text known as man. I have a text known as queen. And I have a text known as woman. Okay. So now let us see the relation. So whatever text you have in your input, it is going to give for battle, whether it is authority, it is going to give 0. Whether it's an event, yes, it is an event, so it is going to give 1. Has tail, completely 0. Battle is rich, 0. And gender is like, for example, this doesn't have any, so we keep 0. Fine. So looking into horse, okay. So for horse authority, there may be some, right? So we can go with 0.01 or something. So based on their relation or importance, it is going to be given. And for example, event is 0. Has tail, yes, absolutely it has, so it is 1. Rich, maybe or may not, so 0.1. And gender, I'll keep it as 1. Then we are going with the word king now. So look at king, authority, yes, 1. Event, 0. Has tail, 0. Rich, maybe rich, right? So maybe like, yeah, we can give 1 here. Gender, king is usually denoted as male, right? For queen, we used to tell, for female, we used to tell them as queen. So we give it as -1. Okay, so -1 is for representing male. And looking at man, authority, there may be some, so we keep 0.2. For event, it is 0. For has tail, it is 0. For rich, it may be something like around 0.3, some values. And gender is -1 because it's representing male now. Looking into queen, queen has authority, yes. Event 0, has tail 0. Rich, yes. Okay, maybe something like 0.2 or 0.4, whatever it could be. Gender is 1 here. It's completely opposite. You can see -1 is for representing male and 1 is for representing female. So look at women now. So for women, we may have something like 0.2 is the relation. 0 here, 0 here, rich. Yeah, maybe. So we give them as, okay, here queen should be something like, it should be completely 1 because queen rich. And women, maybe we can give something like 0.2. And here gender, we will be giving 1. So this is how the words are related. And you can see for male and female, we are giving the respective things. So this is achieved based on training. This is your trained data, and this is your input. So for your input, like this, for different words up to maybe like minimally 300 words, you will be getting an array. It may be from between 0 to 1 based representing their relation. Okay. And one more thing, what you can do is from these words, let us pick a few details from here and then imply. For example, let me take the word king, and let us take the vectors of a king. Maybe we'll do it here with some different color. Yeah. So the word king has a vector. Okay, we'll consider this alone. We have 1, 0, 0, 1 and minus 1. So now what I'm going to do is I'm going to subtract this vector with man. Okay, so we know that the only thing, the difference between king and queen is the gender which is representing. So I'm going to reduce the man here, which is going to be something like the values for man is 0.2, 0, 0, 0.3 and minus 1. Okay, so we are actually subtracting. So when you subtract, we'll be getting a result which will be something like 0.8, 0, 0, 0.7, and then this will be turned into 1. So this will become 0 now. So once I reduce this property, I'm going to add this value with the array of women. Okay, so I'm going now adding the gender women here. So what's the value of women? We have 0.2 and we have 0, here 0, here it is 0.2, here it is 1. So when you add this 2, you will be getting a result. So when you just add this, you will be getting 1 here, 0, 0, 0.9 will be here, and here it is 1. And if you see, this is nothing but this is morely equal to, okay, approximately this is equal to the vector which is 0, 1, 0, 0, 1 and 1, and this is nothing but the vector for the word queen. So we have already seen 1, 0, 0, 1, 1, 1, 0, 0, 1, 1. So you are subtracting from king, the only difference is the gender. So you are subtracting male gender from there, you are adding the property women, and you will be getting the queen. And if we try to get some details like this, then actually our representation works really well and it is going to give us good results. So that's what the idea is about, and this is how our word to vec will work. And not only this, we can also find relation of one word with the other, how related it is. We will be doing it with the help of distance and cosine similarity. Consider not, we are not going to do the complex things. Let us do about simple things, like maybe we'll try to represent them in 2D. In a 2D vector space, let us try to represent words. Let us have some x and y axis. Okay, so we have our x and y axis, and we have 2 points here. So one word is around here, another word is around here. So this word may be something like king, and this word is something like of monarchy, or we'll choose some simple words. Maybe we'll try to find the relation of man here, or simply we can go for kingdom. Okay, so we'll choose kingdom. So we have 2 words, and if you want to find whether they both are related or not, how much, we can use something known as distance. And for finding distance, we have a formula. So the distance between them in this vector space is equal to 1 minus cosine similarity. Cosine similarity. So talking about this cosine similarity, if you want to find it, is nothing but cosine similarity is going to be the angle of your cos value. So first try to draw lines from your coordinates. Okay, so what's the angle? Something like, maybe if it's like 45 degree. So what's the value of cos 45? We substitute it here. So it is 1 by root 2, which is something around 0.7071, I hope so. 0.7071, I hope so. So from here, once you calculate this cos 45 or this value cosine similarity, the distance for you is going to be 1 minus this 0.7071, which tells that it is 0.29 dot dot. And whatever thing you have, if this distance is less or closer to 0, it is going to be more related. So these two are more related. Maybe you have some other word which is something like this. Maybe we make another word. We have a word known as which is here, located here, cricket, and we have another word which is located here, which is something like burger. Okay, so we have 2 words now, and you can see they are not related, we know that. But if you look at, if you represent in this way and try to get the angle, it is going to be like 90 degree, right? So when you calculate this, cos 90 is going to give us 0. And if you calculate the distance now, so it is distance is equal to 1 minus cos 90, which is 0. So distance is equal to 1. And it is not anywhere closer to 0. It is completely opposite, to which tells that these two words are completely unrelated. So in that way, we can carry the meaning of one word with the other, and this is also possible with the help of our word to vec transformations. So with these details, now let us see how these things are achieved actually. This looks great. This works well, this looks fine, but how someone can do this or how it has been achieved? In the upcoming session, we will be doing anyway hands-on or from scratch. We'll see it now. So for example, the vectors we'll see. So the transformation of word to vector from, for example, can be done with the help of either CBOW, which is continuous bag of words, or skipgrams. And first let us start with continuous bag of words. So in continuous bag of words, the model architecture tries to predict the current target word, which is usually people used to keep their center word, is the target based on the source context of the surrounding word it may have. Okay, so once you train the CBOW, it generates numerical vectors known as word embeddings, which captures the semantics of word in a continuous vector space and can be used in various NLP tasks. Consider a simple example with a simple sentence here. So the quick brown fox jumps over the lazy dog. This can be pairs of, like, you have to create a context window and the target word. Maybe if you have go with a size of 2, then word something like, first let us see the context window, which is quick and fox. So we have quick here and fox here. So the target here is going to be the middle word, which is brown. Okay, brown. And then the and brown, the target is quick. You pick the and dog, where it is, we have the here, dog here, it is the middle word, target is going to be lazy. So like this, we create some features by selecting the middle word and keeping the remaining word. So you are actually doing it and finding the middle word as a target. Once you keep it based on this window size, which we can adjust. If you go 3, then for 3 words, you pick the middle word and so on. With these things, what we are going to do is we are going to train a deep learning neural network. We will be doing a artificial neural network training. So what we will be exactly doing is, for example, in CBOW, let us see hope can set you free. This is a word, and you pick the first 3 window size of hope can set, and the target is can, and the vector for hope is here, the set is here, and initially you won't be having any vector, right? So you are creating bag of words here. So in your sentence, hope is coming here, so 1, other things will be 0, and set 0 0 1 0 0, set is there in third place with this bag of words. That's why it's continuous bag of words. Once you have it, you train your model with randomly adjusted with random weights and bias. Usually the prediction will go wrong and it will be some values. When you calculate your loss, you are going to tell the actual target is 1 here. What is 1 here? 1 here is can. So that's what you have to predict. So like this, we are training for each window. So over that time, they are adjusting its weight and bias. So in your entire corpus, it is going to try to set meaning, and over the training they are going to give some weightage for it, and that is what our word embeddings, and that's what we are interested about. That is going to tell the relation whether it is related with one word or not based on the weightage of it. And even in the next session we will be doing something like training on a simple data with limited corpus. But usually Google has done for a GenSim, there is a library. What they have done is they have trained it on billions of words so that each word can find its relation with the other word. So if you train on an entire corpus, a huge amount of dictionary and data, then what we can actually do is for each word we can set some vector representation which is going to help us convey the meaning. That can be really helpful for convey the semantic meaning and make it use in our particular progress. And we have another type as well, which is skipgrams. So before going to skipgrams, let us see some visualization in the whiteboard about our CBOW or continuous bag of words. So it is like this only. Let us see, for example, hope can set you free. Once again, for each word you will be representing the vector and you will train. Let us do this. For example, let us write, for example, hope can set you free. So in the first time you have a window size of this, and this is your target, and for hope and set you are going to create continuous bag of words. Actually, for hope it is going to be 1, everywhere 0. And then for set, the next feature you have, it is going to be in the third place, right? 0 0 1 0 0. So you train your model with neural networks. It could be like 1 or 2 layers. For example, let us have this. So we know that the training will happen. So this is a vector. This is another feature vector. Fine. So we'll be training and the information will be passed here and there. So from here, it is going to map to a particular output, which is going to give us maybe like, for example, let us represent. Usually it will give something like 0.1 or 0.04, 0.2, 0.08, because it's randomly adjusted values, right? 0.02, this is what will be given. But you are going to anyway, you during back propagation, you are going to compare with the error. So when you give the original input, it is going to be 0, 1, 0, 0, 0. So your word should be the second word which you have, can. Okay, so this is what you should predict. So it adjusts. Okay, and then after this, it is going to go into the next set of window, where with the feature can and you, it is going to predict set. And like this window moves over your entire corpus. So you train with a lot of parameters in that way. So that's how this continuous bag of words actually work. Similarly, we have another type which is known as skipgrams. So skipgram is used to predict the context word for a given target word, which means if you give a target word, it is going to predict the surrounding or the context, which is completely reverse or opposite of our continuous bag of words algorithm. Here the target word is the input, while context words are the output. So you are going to predict the context. As there is more than one context word to be predicted, which makes that problem a little bit difficult. Here it will be a little bit difficult because earlier you have other features to predict one word. Now with one word you are predicting the surrounding features. And maybe it will be a bit difficult, and a continuous bag of words model architecture predicts current target word based on current context which is surrounding. Here based on current word, it is going to predict the context as well, and that's their difference. So the skipgram variant takes a target word and tries to predict the surrounding context word, whereas the continuous bag of word variant takes a set of context word and tries to predict a target word. And we will cover the skipgram variant now. For example, you take a word known as wide and you are going to predict what is the surrounding. So it should be something like, for example, here the word wide is trained here, that is 1 in this place. So with this wide, the surrounding should be predicted as the and road. So you are getting multiple outputs. See here, this output, the original you are comparing with 1 here, which is for road, and here you are comparing with 1 in the 0th index, which is for the. So you are predicting both, which is surrounding to it. Then for road, you will be predicting wide and shimmered. For shimmered, it is road and in. So in that way, we calculate the loss and we try to improve and iterate, and that's how skipgrams actually works. Let us see this once again in our notebook as well, in our whiteboard. So here you go with target word. Maybe you are going with can, and you are trying to predict its relation. Okay, so for can, what's the exact representation is 0 1 0 0 0, and now you are mapping or training your neural network to provide 2 vectors. So first vector, maybe like consider this neural network training, information is passed, and finally you are predicting 2 vectors. So the first vector here you have, you will be having some random numbers, 0.2, 0.1, 0, 0.3, 0.5, and you have another vector which is 1, it's like 0.1, 0.2, 0.12, 0.02, 0.9. Okay, so but you have to compare with the original outputs, that this should be for hope, and that should be something like this will be compared with loss. The real value is 1 0 0 0, and the next word it should have is something like, when you compare this hope can set, right? For set it is 0 0 1 0 0. So this is what you need to map. So you train and then you move the next word and choose the next surrounding words and you predict, and that's how skipgrams will work. And this is how we used to train our continuous bag of words and CBOW, and this is how the semantic meaning which is achieved from word to vector. And for example, the words like king and queen may be similar, and if you subtract with king with man and add the property or vectors of women, then you should get the vector of queen, right? So that is the result which we will be expecting, and we can achieve this. And in the next session, especially this word to vec, you can train with a limited amount of data, because you can't train on billion parameters. It will be difficult regarding the infrastructure which we have, and the time constraints and GPU constraints. Anyway, with limited data, you can train your own neural network. You can build from scratch, or you can also do one thing. You can go and use GenSim, where you can download already trained data and use it, or you can get the GenSim and train on your own model. It will be done quickly, which will be updated for your context. So all these things will be